Mike. Okay, hi everybody. Yep, we're time. If you're here, nice to see you. If you're watching later, hope you're having a good week. Next to last week. So, hi baby doll, nice to see you here as always. I had a TA helping me on your, hi Tyler, nice to see you. I had a TA helping me grade your projects, and they fell a little bit behind the deadline I had set for them. So I've just been grading them. So I'm down to the last 3 projects that are ungraded. So apologies that went longer than was planned. We expected to get all those done by Friday last week, but the TA fell behind a little bit. So I'm filling in the gap. So after class tonight, I will probably just stay up and grade those last 3, and everyone will have a grade back. So they're quite difficult to grade. If there's crashing behavior, then we do our best to try to figure out what went wrong. But anyway, just so you know, the last 3 are queued up, and I expect I'm going to try to finish those this evening before I eat dinner. So there's that. Okay, so next to last week, we are in week 16. Okay, so week 16, this is the last component that you need for project 4. So project 4 is a driver that processes a file of inputs, very similar to what we did on project 3. It uses a binary search tree template. And then what we're creating this week is the last component, and it's the thing that goes in the binary search tree. So, and I'm going to do a sample component to put in the binary search tree. And then we'll look at the lab that's directly applicable to the project. Okay, the trick, the new thing, probably for most of you, if not all of you, is doing overloaded operators. So you'll see what that means in just a second, but that comes up immediately if we try to use our binary search tree for a custom component that we create for ourselves. Okay, so Zybook reading, and then I added an extra reading to help you. I just thought of maybe a different presentation other than your book and myself, how to create what are called friend functions, which is one of the ways we're going to create overloaded operators. You'll see that in a bit as well. Okay, so last lab, lab 16. I'm not going to implement this one, but the supplemental videos pretty much guaranteed. Hold on. The supplemental videos will have a walkthrough of the lab, so if you need to see it from start to finish, the supplemental videos will have it. So I'll come back to this. Let's just see what else is going on. A lot of you have already started to post, which is awesome. You're actually doing really nice posts. They're good reading for what test-driven development is and a couple of related issues. So a little research project for the next to last week. Okay, so as always, a lab, a discussion. The final project of the semester is due on Sunday. So next week, we are into kind of bonus lab. So if you look at next week, it has a discussion as always, it has a lab as always. I will lecture as always, but you will be past the project, so it's just one last piece of content. Okay, so I'm actually going to switch over and start working in code. The first thing I need to do is I need to grab my binary search tree. So I'm going to actually, can I fork from here? Doesn't look like I can. So let me grab my binary search tree, which is templated, and that's critical for me doing what it is that I'm about to do. So make a new one. I will call it lab 16, even though I'm not yet doing the lab. Okay, so let me add this file. Okay, so there's my binary search tree. It's templated, which means that I can use it for any kind of data that I want to. Oh, what is the week 17? So Baby Doll's looked, what is week 17? Is that a poll? Oh, okay, I'll go post that after class. Thank you, Baby Doll. I didn't notice that I hadn't put that one out there yet. Actually, I think I may have accidentally deleted that, not remembering what it was. Okay, I'm going to leave that up in a tab so that I remember. So the discussion for week 17 I've accidentally not posted. Okay, so what I've done is I called it Lab 16. I created a new REPL. I copied over my completed binary search tree from Lab 15. And now I'm going to go use it in a program. So include it. So the thing to note here is that I can take my binary search tree and I can use it for any kind of data that I want. Ints, bools wouldn't make a whole lot of sense, but I could in theory use it for strings, assuming I had an include for strings. May want to have the ability to print stuff, so I'll go ahead and put that there. And then I can do, I can insert stuff, -10, 100, and so forth, right? And then I can do itree.print in order, and it should print it. And then I can do strings, so I can say the stree.insert apple print that in reverse order just for fun. So just sort of pointing out to you to get us warmed up a little bit. Yeah, good one, Baby Doll. I just saw that TIL that I hadn't posted week 17 discussion. Okay, so we're kind of getting you warmed up on the idea that I can use the binary search tree template to make a tree of any kind of data that I want. Now, once I'm in that tree, everything in that tree is that kind of data. And let me show you one thing I can do here. So I can, for example, I can grab a pointer to a string what's the API for that? Is it get? Find get. So I can actually get a pointer to, let's say, banana, and I can actually use that. I could dereference it, for example, and I could overwrite it with data. Now it's going to screw up my tree entirely because it will no longer be in order, so you want to be very careful about this. But in theory I can say bananas if I want, and then print it out. So let's see what happens. So there you notice there's the 10 and 100 from the first tree, and then orange, banana, apple, that's in reverse order, and then orange, bananas, apple, because I actually got a pointer into the data inside of a node in the tree and altered the node's contents that way. So I just want you to have those things in mind about this templated class here. Once you set up a tree with a certain kind of data, then you have to be mindful of what the data is so that when you're operating on it, you are operating with the right kind of data in mind. But now let's do something more interesting, and this is sort of the crux This is the crux of project 4, the last component. Let's say that you had, I'll make a class for it. Let's say that you had a custom component in this case, a class called product. And let's give it a name, and we will give it a price. And I'll go ahead and initialize. I should probably just say N. Okay, so I have a little class here called product. I have a constructor that initializes the fields with some data. I have the 2 private members. But now that I've created this custom type product, I can actually make a tree to contain them. So I'm just going to compile that just like that. If I do ptree.print in order, in theory nothing should happen because nothing's in there, but let's try it. Okay, I'm getting major explosion of errors, so let's comment that out first and just build. Okay, so got our tree that will hold products, which are these things. So now you have to think hard. You have a node, it has an object in it, and objects are complex. They have multiple data fields, they have functions. Much like a string has functions attached to it, but this one is off-putting to people at first because it's hard to think that I have a node and there's all this complexity and I have products in the nodes, and how does that work? Remember at this point, we don't care how the tree works. It works. We proved it last week in the lab. The tree works. So all I have to do is get my product to be compliant with the tree's requirements. So I'm actually going to get rid of that. So what I would like to be able to do, for example, is insert products. What I'm doing here, by the way, is called, so I will use Apple as a product. I'll make them be worth 75 cents a pop. This is called an anonymous object. So I create an object. It doesn't have a name or a label associated with it. It just goes straight into a node. Let's see if that compiles. Okay, so we're getting some complaints here, and this brings us up to this week's topic. So look at the complaints. Invalid operands to binary expression. So right here, new data less than troot data. So now I have to think, what is the data we're talking about here, and what is the data in a node? The data is a product. So what it's trying to do is taking a new product and compare it with the product that's inside of a node. And I get an error immediately. Now why is that? The reason why I get an error when I try to compare to see if one product is less than another product is that I just invented product from the clear blue sky. C++ couldn't possibly know what it means to compare one product to another product. So if I want my product to go in my tree, I'm at least going to have to tell C++ what it means for one product to be less than another product. And to do that, we need to be able to overload this less than operator. So here's what that looks like. The function itself returns a bool, and the way you overload it is with the word operator and the operator you're trying to overload. In this case, it's the less than. So the operator less than returns bools, returns trues and falses. Something is either less than something or it's not. So I'm about to overload this operator, meaning I'm about to apply a definition for it for my custom product type. The argument, technically, less than has two arguments. It has the thing on the left and the thing on the right. You don't have to place the thing on the left, but you do have to place the thing on the right. I will call this the other product. Now I'm doing everything inside the class to keep this compressed. Okay, so here I am setting up to define this operator less than for my product class so that it will work in my tree. This other is the right-hand side of the comparison. So when you're overloading operators, you just have to decide what you think it means. I have two choices here. I could cause my products to be sorted by their names or by their prices. That's totally up to me. C++ is simply going to apply the ordering that I define. I'm going to do the names. So I'm going to say, I'm going to return the result of comparing this, that's the left-hand side name, less than the other's name. So since C++ doesn't know what it means to compare a product, I'm just going to tell it what it means is to compare their names that way. See, there's that less than. Now the reason why that works is because these are strings, and C++ knows what it means to compare one string to see if it's less than another string. It alphabetizes them. So what it means to compare two products is to compare their names using the same operator. So a product will come before another one if its name comes before the other one. That's an overloaded less than operator for a product. I'm going to run that. Now I have this problem. The greater than operator wants to be implemented as well. Now I kind of set this up on purpose over time so we would experience this. Great. So I already know how to do that. I will overload that operator for products. And when C++ is asked to compare two products, I will actually just compare their names in the same way. So to compare two products to see if one is greater than another is really to compare to see if one's name is greater than the other's name. Is it running? I don't know. Stop. Run. There we go. What? Okay, it compiled. I think that's all it means, is it compiled this time. So now I'm able to insert stuff. Let's insert a few. Yeah, I'll take this. Let's insert a few more products. Insert some shoes for like 20 bucks. I'll insert some, I don't know, pencil for for 99 cents. Run that. Okay, so it still compiles. Now, let's see what happens if I try to print in order this tree. Okay, I kind of get a wall of errors, but if I scroll up a little bit, I'm going to find the thing that I want. I saw it go by. It's right here. See the green? So that's a nice feature of Replit right here. Invalid operands to binary expression. So what it's saying is it doesn't actually know how to do C-outing on products. I just created product and it doesn't know how to do that operator on product. So I'm going to do the same thing, mostly the same thing, as I did with the other operators. But for this kind of operator, which we call the insertion operator, the way to do that is by creating a friend. Now this one's scary. It's scary looking at first until you studied it for a while. So for this operator specifically, we're going to make a friend function. Its name, let me return type. Its name is operator, so that's nothing new. And then we need to figure out the return type, and these take 2 arguments. So friends are a little bit different because they're not technically actually product functions, they're friend of product functions. So they don't have access to myself, this. They're kind of an outsider who's been allowed in. So let's look at the setup here. So here's the operator. It has 2 things as arguments. The first argument is this output. The second argument is the product. So the second argument is the easy part. I'll just call it P. So the second argument to this special kind of operator, it's a little bit different, is a product. The first one is actually called an O stream. Now here's the funky part. You see how we have these pieces kind of stringing together, so there's n line going in, and then here's data going in, and finally it lands on an output stream. So this O stream means output stream, but it's actually being altered in place. Now this one's just hard, which is why we're doing it together, but this output stream is being altered in place, and the way you can kind of tell that is because you can look at one of these output lines and there's a whole bunch of pieces, right? So there's n line going in, and then added to that is troots data going in, and then sometimes you add more to that, and then you add more to that, and ultimately you get to the final, here you go. So that's why this thing has an ampersand on it, is because we're taking an output stream and we are manipulating it, adding to it as we go, adding more and more and more. So this product is just going to come in and add on to whatever else was already going on inside of it. What it returns, by the way, is more of itself. And that's the same reason. So we take our product, we put it on the output stream, and then we send the output stream along so that more stuff could be added if we wanted to later. This one's really funky, and I don't expect that you're going to feel comfortable with it. This is what they look like. And we do these kinds, these sort of weird output ones, as friends. Okay, so now how do we do that? Well, we take this output stream and pretend like it's Cout. So we'll take the output stream that's our argument and just treat it as if it were Cout. So what would I want to see out about this product? Well, the name, and then probably a space and a $sign, and then the price. I'm not going to put an n-line marker. And then we return the manipulated output stream. I know this one's super funky. This is just the way they work. I need the magic formula, which I don't remember, so I'm going to go get it. There's just other things that I have got in my head. So I'm also going to change the output stream to set the precision on it. So I know this one's super funky, but if you need to cause a custom type to work on a cout like this. By the way, you can also use it to write data into a file. This is how you do it. And we'll look at Word here in a second also. Okay, so with that in place, in theory, my main, which does 3 inserts and then a print in order, might work. Click the button. Okay, there they are. Apple Pencil shoes. It's a little bit like voodoo or like magic. Not every language allows you to do this kind of thing. C++ does. You can literally take what looks like a built-in operator and redefine it for your custom components. That's how that one works. Yeah, so that's the thing. So I'm going to go grab some of the lab code and we'll get a little bit of a start and then I will sort of show it in the context of the project a little bit. So hopefully what I did made sense. Overloading the comparisons is pretty easy. Overloading streams, which is what this O stream is, this is an output stream. Overloading streams is a little bit scarier looking. Once you get on the inside, you just take your out and you pretend as if it were cout. So you've kind of done this with string streams before. I know the setup is just nasty. So there you have it. That's what it looks like. You can overload, by the way, anything that you want. You can overload the plus symbol. You can overload the square brackets. You can overload the parentheses. Yeah, that's right. Baby Doll's exactly right, by the way. You can actually, if you wanted to compare a product with a string, you could do that. As long as the arguments are different, you can overload with different data types. Good point, Baby Doll. It's pretty slick, actually, that you can do that. Okay, so let's go grab some lab code and see what it does. And see if there's anything scary in it. Okay, so it's got a word.h and a word.cpp, so I'm going to grab the word.h file first, repl it, put it in here. Okay, there's word.h. Look, there's some operators. We're kind of familiar with that. And the friend, I called it outs here instead of out, but same idea. Now we need word.cpp, which doesn't have anything in it. Yeah, doesn't have anything in it, except for the include. And I'll just sort of get you started. Okay, so this word class, word.h and word.cpp, this needs to be in your project. So your project should have this same folder structure as this week's lab does. And in fact, if you look at the unit testing code, which I'm not going to run, but if you look at the unit testing code, it actually tests the word class by itself. And it also tests the binary search tree with your word class in it. So you need both of those, all of that stuff for Lab 16. You need your binary search tree from Lab 15. It's already complete. And then you need these 2 Word files, and then you need doc test, and you need the driver. This is just sample code, of course. Okay, so let's go look at default constructor, initialize the word with empty. So this is important for the project. It's also important for the lab. It's really weird looking that the class is called word, and what is its job? Its job is to hold a string and a counter. Now the string is called word. So if you look in the word object, you have a word string, but it's a little w. So big W word class has a little w word string inside of it, and it also has a counter inside of it. also has a helper function for doing some of the work. So this is a word with empty string. That's kind of already auto-magically done. Let me just grab these and let's work through a few of them together. I also need this upper thing. Okay, bunch of cleanup here. All that stuff goes. I might leave that until I implement a little bit. Okay, remember to do this part. So the first thing to do is to stop and just make sure that you understand that the word class is a container for a word string and a counter. Has a equivalency operator in it. Okay, now we do word colon colon on some stuff. Okay, now we hit a weird one. So friends are not members. They're just friends. And since it's been stated to be a friend in the .h file, you don't repeat that. So this one's tricky. You do not put word colon colon on it, and you take the keyword friend off because that's already appeared in the header file, and you don't want it to appear twice. So here's the whole setup for that operator being overloaded. The ampersands, by the way, can go anywhere. I think in the sample I just did, I put them on the other side. They can go anywhere in between. It's fine. So stop and take a look at this, what used to be a friend function. I did not put word colon colon on it because it is not a member of word, it is a friend of word. So keep that in mind. This one is a member, so I do put word colon colon on that, but this one's weird. It's just a friend. And the whole trick about a friend function is that it has direct access, as a friend, it has direct access to the data without having to go through a function call. That's the whole advantage of it being a friend, is that it can actually, without altering the data, it can directly access the data. So it's weird, but you'll see it again. Okay, so we can do some of the low-hanging fruit kind of stuff. So here's the little, that's the string member of the class word, has a string in it that starts empty. What? I think I want mine, but I don't know. Something's being weird. I'm checking. Okay, I think it's okay. What was that counter called? It's called count. So make sure the count starts at. Oh, that's interesting. So Baby Doll's seen that before. I've actually, I've never seen that specific thing before, which is interesting. Oh, and Little Peeper's seen that weird thing. Huh. I guess they're probably just experiencing heavy workload or something. All right, you guys can go up there. Okay, so it tells me to initialize the word with an empty string. So this is the string data member. Starts out as nothing, and the count, I did that wrong, it's supposed to start at 1. Okay, this one, with this word parameter and an account of 1, although in this case it says it's supposed to convert the parameter to all uppercase. So I am not going to use an initializer list because I want to use my function down here that takes a string and returns a string that's all uppercase. So we're going to say this word equals upper the argument word per the note. Oh, so Little Peeper sees that problem a lot. I was having it when I was grading earlier, but I'd never seen specifically that. Do you want to keep yours? Or so that's interesting. Oh, and then count. Count equals 1. Okay, so this one's a little bit different because I'm told in the notes, uppercase the word that you get. This one is uppercased, and then I store it as the member. Remember, that's the string part, and then the counter is 1. Okay, so that one's a little bit different. I'm going to leave that alone. I'm going to do this just the super... actually, I'll let you look up how to do that. There's a couple of different ways how to do it, but I shouldn't do every last little tiny thing. So set word, I'm not going to implement it, but I want you to notice, converts the string, this word, to all uppercase. So I'm going to have to do that again. Get the word is just return this guy. Get the count, return this guy. Increment the count is literally what it means. That's it. Just increment the count. Okay, equals. So I'll give you one hint about this on this one. So returns true if the string attributes are equivalent. So if I'm trying to compare two words, well, simply tell C++, actually just take our words and see if those are equivalent. Notice, by the way, this is a pointer and target is not. So, hint, hint, convert the operator on word to do that same operator on their strings, on their little w words. Same for less than. Okay, so this one says, as an example, print the little w word followed by a space followed by the count. Well, that's pretty easy. I'm given this source and this output stream, so I'll just treat that output stream as if it were cout. So I will take the sources word. The fact that I can say source.word outside of a word class function is because this is a friend. So a friend can actually get at the data directly without using a function call. Followed by a space, followed by the count. That's it. And then I return the output stream because that's how this operator works. So that's pretty darned easy. Okay, so I'm leaving some holes there. If you totally get stuck, probably the second of the supplemental videos has a complete walkthrough start to finish if I had to guess. But I think you can do it, so I'm going to leave those for you to have a crack at for yourself. We did the tough stuff. And then that one, there's a couple of different ways that you can do it. Okay, so the main thing is I wanted you to, at least from this perspective, the lab is really about completing the implementation of this word. Now, why do you want that? Because your project needs it. So let me make a notes file and talk about how this is going to work in the project. So I'm just moving that driver stuff to notes, and then I'm going to do some pseudocode. So in your project, I'm struggling here. You're going to need both of these components in your project. So pseudocode for project 4. So this would be kind of where you would start with project 4. So what I want to do is How are we doing on time? We're doing fine on time. I want to show you how you would apply this in the project. So we're going to have an int main. We're going to do file opening stuff. Command line argument stuff. File opening stuff. Yeah, so there's a good chance you're going to, Baby Doll saying that there's, yeah, you're going to need, you're going to need some C++ library include. So in the chat, you might see that Baby Dolls, and you're correct. You're probably going to need IOStream, FStream, and string includes to polish this off. So this is pseudocode. You're probably going to need additional includes, but I want you to note that you need both of those things as includes. You need your completed BS tree .hpp from lab 15. You need your completed word .h included from lab 16. You need both word source files, word.h and word.cpp. You need bstree.cpp, and you need main, which will be your driver that has the run through the file and all that stuff, right? So while getting lines from the file, ... So you're going to have, let's look at what the commands are real quick. I have forgotten. I need that open. Here's a link. Let's go see what the commands are. The operations. I want to show you specifically insert. I actually probably find maybe all of these, I, F, R, and G. Okay, so what does that look like? Oh, there it was. Did you see there's a little lag there? All right, so these are the tricky ones because you haven't done this before. So we're getting lines from a file and we're doing, you know, if next line dot app 0 equals I. Up here, of course, we're going to have so a dynamic tree of word objects. Okay, so in the case of inserting, so this one's tricky on this tree because the tree will not allow the same word in there twice. So to do an insert, you actually need to check and see if the thing's already in there so that you don't lose information. So here's how you should do it. Of course, you're going to check first to make sure tree is not null, right? So I'm going to pretend like I did that. Else, so this would be the else part. So first thing is string little w word is next line dot substring everything starting from the second character over, right? So we skip the command, we skip a space, and we get a string. It's going to look something like this coming from the file. So we got the I part off, and then we went 0, 1, 2, and we've got everything from character 2 to the end of the line, which is the little w word itself, the string. So now I have the little w word itself. Now what I have to do is I'm going to make a product for it. using that overloaded constructor that we did. Now I have to do this. I don't want to put this word in there twice, but if apple is already in my tree, if the product word, if the word, the big W word containing the string word is already in my tree, then I want to update the counter so that I know that I've seen an attempt to insert this more than one time, but I don't actually insert the whole object again, I just increment its counter. So you have an operation in your tree that lets you do this. So they want to insert apple. Well, I'm going to make a word object to contain it, and then I'm going to go see if I can find it. Let's just do it right here. Okay, so I'm going to see if the tree can get me a pointer to that word. Now the whole trick to BS tree get, let's go look at it. What's going to happen? It's going to use the recursive one. Where are you? Here it is. So it's going to go looking for my data. If it falls off the tree, I'm going to get a null pointer back, and that's good news because that means I can insert the thing that I want. But ultimately, if it finds a match, it's going to return to me a pointer to one of those words that has the string that I'm trying to insert already in it. I'm about to, I should have had my camera on, so that but I don't. So I don't know if I can do that without breaking the stream. I'll try. Okay, so the process in this project of inserting a word is hard. We've got to get the string itself. I'm going to build a word object to contain it. So we have this word object that has apple, all capitalized, and counter of 1. But then I'm going to go see if the tree already has that word. And I know that the way it does that is by comparing the strings. So it's looking for a node that has a word object in it that says apple. If there is, it's going to return me a pointer to that. So now I say if p-word is not equal to null, that means that I've already got a word object with apple in it. And then all I'm going to do is increment. What was that called? Increment count. Increment count. So if I've already got an object in my tree that has apple in it, I will just increment its counter. So now it will say, oh, you've inserted apple 2 times. You only get 1 apple object, but its counter says 2, which means that we know we've seen it 2 times. If it can't find a pointer to a word that has apple in it, that means it's not there, and I will simply say tree.insert that newly created object. Kind of crazy. That's a hard one. So that's the whole process. Hopefully that gives you enough to sort of reason it out. Probably if you look at the supplemental videos, there's extra drawings and stuff. I will see if I can get my camera to function with OBS already running. So you can see that. Let me go through these commands first and then I'll try a picture. Yeah, you can do those, but really you just need else, right? So if you try to get that word from the tree and you get a null pointer back, then you know it wasn't in there. In this case, you didn't get a null pointer back, which means it is in there, which means that you simply go in there and you increment the counter, but don't change the word. Otherwise, you know it's safe to go ahead and insert that newly created word. Okay, so find. Oh, I see what maybe you're doing the else if. Maybe doll, you're already on this one. Check for non-existent tree. Yeah, so baby doll, you did an extra step that you didn't need, but keep that in mind what you just said, because you've already sort of worked out the find logic. So if the command is find, you're being given strings and you have to convert those into word objects. So the first thing you need to do is make yourself a word object. To contain that word, and now you can go hunt it down in the tree. So now you can say if tree.find w found, else not found. So what I'm kind of building you up to here is that these commands that have a string attached to them, you have to get the string out. You have to make a word object to hold that string, because that's what's in the tree, and then you can go use that word object to see if you can find a match in the tree. And remember that word objects, the reality is that they are converting their comparisons into comparing just the words, just the strings inside of themselves. But you don't really have to think about that from here. You just got to get the string, put it in an object, and then send the object into the tree. Remove. So same idea. Right, it's going to look like this. So this is saying remove that object that contains that string inside of it, sort of like an extra layer. I'm going to get rid of the middleman this time. So remember, the first thing is you need to make a word object and put this string inside of it. So I'm just going to eliminate the middleman here and go straight to grabbing the substring and just make the word with it. So you can do it either way. Up here I did it in 2 steps. I grabbed the string from the file and then I put it in a word object. Here I just did it all in one fell swoop. Then we can say if tree.remove the object, because the tree contains objects, so every time that you send something into the tree, it needs to be an object. Hopefully that makes sense. So this get I'm not sure what does it want you to do. What does get want you to do? Get word. Okay, but let's look at the required output for get. Got w count. Okay, so got w count or not found or tree empty. Okay. So same thing. So check first. Right, and I'm just doing a little example here. This might be what it looked like. So I make a word object, pull that string that I got, that I got from reading the file. Now this time, it's asking me to do a get. So I'm going to see if I can get, and the get returns a pointer to one of those objects inside of a node, remember. So I have this word set up, but it's because I need to tell the tree to go get the word inside of it, hopefully, that matches. And then I can check. So if p word is not null, that means success. I would do something like cout got dereference P word. Now the trick here, the reason why I can dereference that pointer and cause it to print out on this operator is because we overloaded it. So the fact that I can say got apple 2 here per the notes is because I overloaded that operator. That's because I did this. It doesn't take a pointer to a word, so I had to dereference it, but that's how I get away with that. Else, not found. So that's also kind of a nice way to make your life easier. So I wanted you to see all of those because you have to, those are all the commands that have a string in the input file. I'll go show you real quick. So sample input. So see, here's an R. So it's trying to insert apple. So in your driver, you have to take this string, extract it with substring, put it into a Word object, and then insert it into the tree. But remember, for insert, that one's special. So make sure that you've carefully watched that part of the video. Okay, but let me just, at least without, well, let's see. Let me see if I can get my camera. Yes, so Baby Doll asks, so yeah, Baby Doll asked, so you could do this. And then I'm going to steal your code. So you could do this, and it's perfectly fine. So that's not a problem if you want to do it that way. But because you have that overloaded operator, you have the choice. So that's these are alternatives. They both would work just fine. So that's fine to do it that way. I'll update these so people are watching to match my pointer name. But since you have the overloaded operator, you can just actually make the word object do it for itself. Totally up to you. But it is kind of neat that you can do that. Okay, so those are those things. What else was I going to do? Oh, I was going to see real quick if I can get my camera to work and draw a picture real quick. So let me just do, let me go to my notes and just add some stuff at the top. Okay, so if you were to have insert or try to insert that same object twice, and then you were to call print in order, the output would be, there would only be one node created because on the second insert, well, if we did our we'd have to do the whole thing. I'll go ahead and do the whole thing. What the heck? So this is like our, so we'd say if keyword not null okay, so this second one is of course going to find the word apple in there, so it's going to increment its count and not insert a brand new node. So what you would get with output is one node that has a count 2 in it, because its count was incremented on the second insert. Let me see if I can get my camera and then I'll quit for the night. Okay, it's 7, so if you have patience, I can go for just a couple more minutes and see if I can get my camera to show up for you. My guess is if I click on camera now, nothing, right? Yeah, nothing right now. So okay, can do it. So let me just draw you a picture to try to help you understand what's going on in Project 4, which is, I know, a little bit weird. Okay, so dock camera. I need a window capture here. Okay, so let me just draw a picture real quick of, I know it's not as good as normal, but I forgot to set it up first. Okay, so let's say that we do, if we were to do our process and insert apple and then insert banana. This is kind of pseudocode drawing. So we insert apple, we insert banana, we insert apple. What we want to have happen is that we end up with a tree that at the first insert has a word in it that has apple and count of 1. So that is what we would get on the first insert. Now on the second insert, we'd end up with banana, which comes after apple. So we get banana 1 as its right child, because it's ordering them based on the strings, because we overloaded that operator. Now if we try to insert apple again, technically it would fail because it would find that that's already in there. But because we have the extra logic in our driver, what we want to do instead is say, oh, I already have an apple, so instead of trying to add an apple, I will increment its count. So what our driver is going to do is it's actually using these counts to know when it's seen an occurrence of that word however many times. So it's seen apple being inserted twice, but it only creates 1 node and then uses the counter to keep track of how many times it's seen it on an insert. So if you were to remove apple, it removes the whole thing. So if we were to remove apple, it does not decrement the count. It literally just wipes out the whole node, and we'd end up with banana being at the root. So hopefully that helps a little bit. Probably, if you look at the supplemental videos, I've probably drawn additional pictures. So anyway, that's that. Okay, I think that does it for me. I've got 3 projects remaining. Sorry to you 3 who haven't got your grade yet. I probably will try to get them to them before I eat dinner tonight. So hopefully I'll get the last 3 done here in a few moments. Anyway, so project on Sunday, don't forget, Piazza. You have great classmates to help on Piazza. In a pinch, schedule a Confer Zoom with me if you need to meet with me and all of my, and I don't have schedule for Confer Zoom, send me a Canvas inbox message and we will schedule one. Otherwise, good luck on the project. After this lab, you have all the components you need. It's just then a matter of putting your driver together, and you have lots of practice from Project 3 on doing something very similar. So hopefully it goes very well for you, and you finish your last project feeling confident. And next week, we're kind of into bonus material, if you will. It's one more lab, and then we're done. So thank you, little people. Appreciate it. Yeah, have a good night. Thanks, Damien, Baby Doll, Tyler. Everyone have a great week. And going into the last week of classes, which normally would be finals week, but We've been instructed to treat it like just another week of instruction this time, so that's what we will do in our class. One more lab. We'll work through it together. It's a pretty interesting concept, and I'll try to cram in a couple of a little bit of bonus material while we're at it. So have a great night. Have a great week. Get in touch if you need any assistance. Yeah, Lab 17 is super cool. It's a really neat concept. Okay, so that's it for me. I will enable the week 17 discussion, upload the videos, finish grading the projects, and we should be good to go. So have a good night.